Hey guys, Mr. Betts here. In the last topic, I talked about the area problem and how that's going to motivate most of the rest of calculus. And what I want to talk about here is how we're going to solve the area problem, or at least begin solving the area problem. You'll see soon that we're not going to come up with a complete solution for it, but we'll get pretty close and we'll be on the right path to coming up with a complete solution for it. So first of all, if we're solving the area problem here, we want to find the area between a function and the x-axis, or in this case, the time axis. We're looking for the area of something that looks like this. We can actually do that using simple geometry. We could break it up into different pieces that are easy to find the areas of, or even this being a trapezoid here, we can find the area of this using the area of a trapezoid, which is the average of the bases times the height. And that's going to give us an area of 90. So this is something that we can do in a pretty straightforward way with some functions. However, most of the functions that we deal with, geometry is just not going to work very well. So we can't find the area of a shape that looks like this using the simple geometric formulas that we learned in geometry class. So if we want to find this area here, we don't have a formula that does that for us. So what we're going to do is we're going to look at ways that we're going to approximate this area. We can get pretty close using shapes that we are familiar with. So the idea here is we're going to divide it into smaller pieces, and we're going to try to find the areas of those smaller pieces, or at least approximate the areas of those smaller pieces, and then add all those areas together. So for example, if I were trying to do this problem here, what I might do, and I'm going to do this in a kind of rudimentary way here, I'm going to split it up into 4 subintervals. So the interval from 0 to 2, we call that just the interval. We're going to break it up into subintervals, which just means smaller intervals within the interval. And what we can do here is we can take each one, and you might think this seems kind of silly because this isn't a very good approximation, but I'm going to approximate the first subinterval using this rectangle. And there's a reason that I use that rectangle. I'll talk about it in a minute. In the second one, I'll use this rectangle here. In the third one, I'll use this rectangle here. And in the fourth one, I'll use this rectangle here. Now, it's pretty obvious that the areas that I get here are not going to add up to the total area under the curve that I'm looking for. However, we can see that it's an under approximation. However, it's going to get us pretty close. We can see that there are gaps. So these gaps are what we call error. So there's gaps here, and it looks like even a little bit of an over approximation there, and a little bit too small here. But we can find the areas of these things pretty easily. We can find the height of, I'm going to go back to the very first rectangle here. Let's just focus on that one. We can find the height of this rectangle right here by using the value of the function at t equals 0. It looks like that's 25, so the area is going to be 25 times the width, which is 1/2. So this rectangle right here has an area of 25 halves, or 12.5, or however you want to think about that. We can find the heights of these rectangles using this method here by using the value of the function. So this right here is going to be f of 1/2. And this height right here is going to be f of 1. So we can find the heights of rectangles by using the value of the function. So even though my approximation wasn't great, I can get a precise area for my approximation, at least by using the function itself. I can make this approximation better by maybe choosing a different point along the way. So instead of choosing a point on the left endpoint, let's say in this first subinterval here, instead of choosing this point, maybe we choose the right endpoint, and we use that as the height of the rectangle. And that looks like it might be a little bit better for this subinterval. We might use, instead of the left endpoint or the right endpoint, we might use the point in the middle, and then use that to make a rectangle. Again, you can see that's going to be a little bit off, but all of these rectangles are pretty close to the area that we're actually trying to approximate, which is this area right here. So we can break this down into shapes that we can find the areas of easily using geometric formulas, and then add those areas together. So there's some structured methods that we're going to use to do this. We're going to look at different ways we can use rectangles, and then we're also going to look at a way that we can use trapezoids instead of rectangles. So if we're going to use rectangles, I've already gone through some examples here, but let's say that we're on a subinterval right here. If I want to approximate the area with that subinterval by using this point on the function right here, since that's the left endpoint, we're going to call these left rectangles. And the method that we're using then is called the left rectangular approximation method. Instead, if I want to use points on the right side, that's going to be using right rectangles. So it's going to be the right rectangular approximation method. Or I might use a point halfway in between, which oftentimes is a better approximation, is the best approximation. It's also oftentimes sometimes the trickiest to work with. So there are trade-offs often by choosing one over another. Sometimes we're looking for not necessarily the best approximation at this point, but we're looking for the one that's the easiest to do. All of these approximations can be made more accurate by using more subintervals. So rather than, say, splitting it up into 4 subintervals, regardless of the method that I'm using, I can expect to get a better approximation by splitting it up into, say, 8 rectangles instead of 4. Or into, I'm not going to do this all the way, but splitting it up into 16 rectangles instead of 8. So even if I'm using an approximation that I know is going to be a little bit off, I know I can also make it a little bit more accurate by using more and more rectangles. So let's look at these in a little bit more specifically. So this one right here, since I'm using the left endpoints, is called the left rectangular approximation method. And I'll have that on the last screen for you to write down. And essentially the idea here is if we pick any single rectangle, say I'm going to pick this one here for simplicity, this one right here, what we can do to find the area of this rectangle is we take the width of the rectangle. This width right here, we're going to call delta x because it's a change along the x-axis. So we're going to take the width, which is delta x, times the height, which is the value of the function at some point. In this particular example, the width is going to be 1/4, and we're taking the value of the function at 1 because that happens to be the x-coordinate, or the t-coordinate in this case, of the left endpoint. So if we knew what the function was, then we could plug 1 into the function and multiply 1/4 times the function, and that gives us the area of that rectangle. On a graph here, we might just approximate it using the graph, and it looks like the height is going to be on that line there, which is about, looks like 42.5. So we can approximate it using the graph also, if that's all we have to go off of. If we use the right endpoints, that's going to be called the right rectangular approximation method. And we can find, again, the area of any one of these by multiplying the value of the function at the point by the width of the interval. So to find the area of this rectangle here, that's going to be delta x, which is 1/4, times the value of the function at, looks like it's going to be 5/4 in this case. And to find the area of the whole thing, or an approximation of the whole thing, we're going to be adding that together with all of the other areas of rectangles. And that area, what I have shaded here, is going to be a decent approximation for the area of the what's under the curve. We could also, and I mentioned this earlier, we could also choose, instead of the left endpoint or the right endpoint, we could choose a midpoint. Now, just for simplicity, I only used 4 subintervals instead of 8 that I did here. And so if the width of the interval is 1/2, then we have to consider that the value that we're evaluating the function at is halfway between the two endpoints. So if we're going on the interval from 0 to 1/2, the value of this, the height, is going to be f of 1/4. And then we're going to multiply that by the width of the interval, which is 1/2. So you can see here that there's different ways that we can approximate this. All of them are going to be a little bit off. They're all going to have some error, but we can also, in the future, get rid of some of that error and improve our estimate by using more and more of them. Now I want to talk about one more method here, and that's using trapezoids. Again, for simplicity, I only used 4 subintervals. And if I want to find the area of any one of these trapezoids, say this one right here, these vertical parts are parallel to each other. So if you remember the area of a trapezoid, any particular trapezoid is the average of the bases times the height. Well, in this case, the height is going to be the width. So in this particular trapezoid, the average of the bases is going to be the value of the function here plus the value of the function here. So f of 1/2 plus f of 1 divided by 2, and then times the width of the interval, which is 1/2. So again, if we know what f of 1/2 is, we know what f of 1 is, then we can find the area of that trapezoid, and then we add that to the areas of the other trapezoids, and we get an approximation for the area of the entire thing. So quick summary here. So first of all, the big idea, I already talked about this. The idea here is we're taking an interval, we're going to divide it into smaller pieces. We're going to approximate the area of each of those pieces and then add all those together to approximate an entire area. So the 4 methods that we're going to use are called the right rectangular approximation method, which I will abbreviate RRAM, left rectangular approximation method, LRAM, midpoint rectangular approximation method, MRAM, and then the trapezoidal approximation, which is TAM. Again, they're all going to have some errors. None of them are going to be perfect, except in special cases. You saw the very first example I did. We used one single trapezoid, and that gave us the exact area. That's going to be rare. That's not going to happen very often. So they're all going to have some errors, but we can improve upon those errors, and we can get a little bit more information about what that error is going to look like, whether it's too big or too small sometimes, based on some information we know about the function, and I'll talk about that in the next video.